So the second part, so the first part, I guess I showed you a few examples where lower bounds, actually tight lower bounds, were proven by cleverly designing some kind of protocol, right? So we really proved an upper bound, but then inverted what we proved to obtain a lower bound. So more on this proving lower bounds via upper bounds will be seen here, and in particular, I'm going to talk about this very important paradigm for proving lower bounds in communication complexity, which is called information complexity paradigm. I want to remind you of something that I said just in words, that this is meant to be tutorial style, and my goal here is to just show you a diversity of results that use the information complexity paradigm, and to maybe not prove these results in great detail like we've been doing so far, but to at least extract the common patterns that come up in applying the information complexity paradigm. So this is hopefully something that's different, or actually kind of orthogonal to stuff that was covered earlier in the beginning workshop in this semester. Okay, so I'm not trying to be comprehensive here about results, and I'm certainly not trying to present the latest results. Okay, so probably the most latest result that I will present here is from 2012 or so. All right, so the paradigm is used for proving lower bounds which have the following form, okay, maybe in some loose sense. So there's two different tasks. So there's task A, which is some kind of simple computational task, and there's task B, which is a compound task that consists of or somehow combines n independent copies of task A. Okay, so under these circumstances, a direct sum theorem will be something that says that the complexity of task B is, it's growing as the number of instances, so omega n times the complexity of A. Okay? Now that isn't always true, but when it is true, we say that there is a direct sum theorem, right? So the paradigm for proving such a theorem using information complexity will be as follows. There's always going to be 3 steps, okay, 1, 2, 3 like this, okay. The first step will be to define some notion of information cost. And like I was saying in part 1, every time you define a cost measure, you have a corresponding complexity measure on functions. So our definition will fairly naturally show that the complexity of task B is at least the information complexity of B. Okay, so when you see a definition, you'll see why this is true, but it will always be sort of obviously true. In part 2 will be to do a simulation argument. This is sort of the main part of showing the direct sum, which says that solving B is equivalent to solving, or not equivalent, maybe solving B entails solving each of these copies of A. Okay, this will be clearer when you see an application of this paradigm, but let's just keep this in mind that this is what's happening. The net result of step 2 will be to show that the information complexity of B is at least n times the information complexity of A, because whenever something like this is true, then by again some kind of easy information theory, you get such an inequality. Okay. So to be sure that the hard work will be showing this first part. Okay, the implication is usually straightforward from information theory. Then finally, so if you combine parts 1 and 2, you get that the complexity of B is at least n times the information complexity of A. But we want to prove that it's at least n times the complexity of A in the original notion of complexity. So we have to prove some kind of reverse inequality. Okay, so this inequality is kind of the reverse of that, right? And maybe it's only true approximately. Hopefully we can prove this reverse inequality because, well, we only have a simple task A here. So maybe we can do it by some ad hoc means. Yeah.
So looking at it.
Yeah.
So what's known for task B solving not n independent copies with some small bias and
Yeah, possibly slightly dependent. There's.
Is there any result?
I don't know that there is a general result, but but actually there are instances of direct sum like theorems that are used in that situation that I know of, coming from this Guruswamy and Onak thing on some kind of pointer chasing. Yeah, they proved, yeah, because they had to prove something like they had to prove something like a direct sum with some dependence between the copies.
Also, if you just look at the proof where you embed, that you'll talk about that as long as you match up the conditional distributions, maybe it doesn't have to.
Yeah, that's true. It doesn't. Yeah, that's true. That's true. It doesn't. Yeah.
But those are all still relying on. They're almost going the same route. That it's almost independent. we are doing the work that
Mhm,
is
mhm.
almost independent, right? As in based on
But when you say small bias, I assume that's what you mean, right? Okay, so I'm not clear on what you mean otherwise, but yeah.
without going through proving this conditional independence or something, without
Yeah, so I don't know. Okay, well, let's see some uses of this paradigm, okay, and then you'll see. But I admit that none of the examples I have here is going to address what you're saying. I think that's the case. But anyway, let's see some of these examples, then maybe we can be clearer on what would be different in what you're suggesting. Although, do you have a concrete problem in mind? Then we can maybe talk about it at the end. Yeah. All right. Anyway, let's see what's going on here. Right. So we'll see examples of this paradigm, right? And as I said, this part will have 3 chapters. Okay. So in chapter 1, we'll look at no interaction situations. Okay. So for example, one way. So we'll start with what is the most basic result in this paradigm, and actually one of the basic results in communication complexity, which is so this concerns the index problem. In the index problem, Alice has n bits, Bob has an index from 1 up to n, and the goal is to just find the bit indexed by find xi, where Alice's string is x and Bob's I. All right. So the usual correctness requirements apply. We're going to consider the general epsilon error case rather than just the 1/3 error case, because it'll be interesting to work out the dependence of the complexity on the error. All right. So the theorem due to Ablayev is that Alice needs to send omega n number of bits to enable this. Fairly well known theorem, but let's actually look at its proof in detail. Okay, and this is also the only time that I will actually run through all the steps of the paradigm in complete detail, because in this simple case it's actually possible to show all the details. All right. So we have to set up a direct sum like situation. So we have to have 2 tasks, a simple task and a complex task. So our simple task will be the following thing. Alice holds a bit b, single bit. Bob holds nothing. And the problem is for Bob to output that same bit as Alice. Okay, so Alice is going to send Bob a message, after which he must output the same bit. Okay, so that's our complex task. So notice that the index problem is something like combining n independent copies of this echo problem, right? So it's not literally solving n copies of it, but it's something like that, right? It somehow combines n copies, and that's enough. That's enough for applying the paradigm. Okay, so we have these 3 steps. So first, we're going to define a suitable notion of information cost. Okay. Now, so the generic idea is information cost should be defined as the amount of information about the input revealed by the messages in the protocol. Okay, and we may say that it's the amount of information about only some part of the input. We can choose which part. Maybe we only consider some of the messages in the protocol, and so on and so forth. Okay, so there's a lot of flexibility in how exactly we define this. Okay. Now, if some of you went to the talks of, I guess, Anup Rao and Omri Weinstein earlier in the semester, you may have seen a very particular definition of information cost, but I want to take a more flexible view that depending on the problem at hand, we can choose to define things one way or the other. All right, now in this case, let pi sub b be a protocol for task b, which is our complex task index. Okay. And we'll define these 3 random variables, x, which is a input distribution for Alice, according to some distribution, says let's say mu, then r, which is the random coins that Alice uses in sending her message, and then m, which is the message generated from input x and random coins r, right? So then the information cost is defined as, we are going to define it as the mutual information between x and m. Okay? So this captures how much Alice's message actually reveals about her input, right? And now notice that by definition, the information cost is at most entropy of m, which is at most the length of m in bits, which is the cost, right, of this protocol. So information cost is less than or equal to cost, and as I said, this almost always, if you define things right, this will follow from easy information theory like that. Okay, now let's do the simulation argument. This is sort of the heart of the proof. So let's take an n-bit input for the index problem. Okay, and let's say it's distributed according to this product distribution IID. So each coordinate is IID distributed according to mu. You can even think of mu as uniform, so it's fine. At any rate, the important part is x1 through xn are independent if it's done like that. So we can write these inequalities down. So first of all, we already have this, cost is greater than I cost. So I cost, this is by definition this mutual information, which is greater than or equal to the sum by the independence of x1 through xn, right? Okay. Now we are going to do something. We have n terms over here, right, in this sum. We are going to do something to realize each term as the information cost of some protocol. And these protocols will be solving the echo problem. So we are going to go about designing n different protocols for the echo problem, where the jth protocol has information cost exactly I x j m in this sum. Okay. Okay. So how do we do this? So we're going to say we have this protocol for the equality problem. For the index problem. Okay. So the big problem. We're going to use this to solve the small problem echo. Okay. Now this may seem backwards. We're using a protocol for a big thing like index to solve a small thing like echo, but that is exactly what we want to do, right? So consider the execution of the index protocol over here, and let's feed it the following type of input. Okay. So we're going to solve the echo problem. So we have our input b. This is our actual input. Now we are going to generate an input for the index problem by plugging in this b into, let's say, the ith position. In this example, I equals 2, let's say. So we plug in this b into the second position, and then we just fill the rest with random bits, okay, distributed according to mu. Then we go about simulating whatever it is that Alice would have done in the index problem. So we send that message, and Bob on his part, see, Bob has no input in the echo problem, right? So the situation in the echo problem is Bob has no input. Now here he's going to pretend that he has the input 2. Okay. The net effect of executing the index protocol is then to extract the second bit, and that is exactly what you have to do in the echo problem. All right, so it's clear that this complicated protocol, well, seemingly needlessly complicated protocol, actually does solve the echo problem correctly, assuming the original protocol solves index. But more importantly than that, the distribution of this message when b is random is exactly the same as the distribution of the message here when you feed it a completely random input, okay, by construction. So it follows that this m by construction, this is m is Alice's message in the index protocol, is distributed the same as Alice's message in our now contrived protocol. Okay. All right, and we have shown that this actually solves the echo problem. Okay, so the net result is this I cost is realized, or this mutual information term is realized as I cost. Okay. Okay, so what have we got? We've got so far that the randomized one-way complexity of task B, which is the index, is at least its information cost, and then the information cost of task B is at least n times the information cost of this echo problem. Okay. So I guess it should be intuitively clear that the echo problem is a non-trivial problem, and so it has some non-zero information cost, and this would give us the omega n lower bound. But if you're not quite happy with that kind of intuitive argument, well, you shouldn't be happy. You should say exactly what is that non-zero quantity. Okay, so we can work it out exactly. So here's how we can work it out. So now let's just consider a protocol for the echo problem. Okay. So let's look at it. We're studying its information cost. How much information cost must this incur? So let Z be a random input for Alice, and let M be the message generated. And let m superscript little z tell us the message generated for a specific input little z. Okay, so there's only two such inputs, 0 and 1. Okay, so this gives us basically two possible random variables, m0 and m1. Okay, so in what comes up, I'm going to use various notions of distance between distributions, and because you tend to use slightly different notations for these, let me put down my notation. So d sub tv will be total variation distance, the standard statistical distance, whatever. dkl will be Kullback-Leibler divergence, also known as relative entropy. Some people write this as just d without any subscripts, but because I have other distances, I'm writing this. There's Jensen-Shannon divergence. If you don't know what that is, it will come up in just a moment. And at some point, we'll use the binary entropy function, so entropy function of a single real variable. Okay. Okay, fine. So by basic information theory, you can work out exactly what the mutual information is in this case, and it is this. It's the average of the following two KL divergences. So the message distribution on input 0 relative to the message distribution on a random input, and then distribution on input 1 relative to random input. Okay. So this average is exactly the Jensen-Shannon divergence between M0 and M1. That's the definition of JS divergence. Here is a potentially heavy hammer that we are using, but this is really an analytic inequality. Okay, so it tells us that the JS divergence between two distributions is greater than or equal to this particular function, right? And the way this is proved is basically calculus at some level. Okay, you have to trust me on this, that this is just an inequality about real functions and some kind of convexity and so on and so forth. It's going to be used. That is what is used. Okay. So anyhow, you can use this to say the following. So if the protocol's error is at most epsilon, then it means that the two message distributions have to have statistical distance of at least 1 minus 2 epsilon, because Bob is supposed to be able to use this message and tell you whether Alice had a 0 or a 1. So Bob should be able to distinguish these two cases, right? And so this means if you plug this in over here and use whatever the convexity, not convexity, in this case just monotonicity, then you get this result, right? So this tells us that the complexity of index in one way is, with error epsilon, is n times this specific constant, 1 minus h of epsilon. That is actually tight. You can achieve that as an upper bound. And maybe an interesting puzzle to figure out how. Okay. So we have just run through the paradigm fully, all 3 steps. I just want to tell you in passing that it seems we have proved a lower bound for a kind of toy problem, but actually this has lots of applications. So there's again a whole bunch of data stream applications. Perhaps you will see 1 or 2 during these 2 weeks. There are data structure lower bounds, which I think came before this week. There was a couple of weeks on fundamental inequalities, which may have addressed some of those. Anyhow, I should point out that the index problem is simple, and often reductions from the index problem are themselves simple, but once in a while the reduction is complicated, right? So the real work is in coming up with the right reduction from index to whatever your streaming problem is. And a good example of this is lower bound on computing the diameter of a streamed graph. Okay, so I just put it out there for somebody who wants to see an interesting application of index. Okay. So there are some extensions of this lower bound. If you consider this problem called augmented index, I believe the term augmented index was invented by David. Is that right? Probably before your paper it wasn't called this, but anyway. All right. Anyhow, so here's what it is. So it's like index, except that Bob not only has the index k that he would like to retrieve, he also has the prefix x1 through xk minus 1 of all previous bits from Alice. He didn't, the term augmented index. Yeah, that's all I'm saying. Yeah, of course it's in his paper. So not this argument though. Yeah, not this, and therefore not the tight constant. So if you look at his paper, yeah. So anyhow, so all I'm saying is you can prove the same lower bound that we just showed for augmented index 2, except that in step 2 of the paradigm, where we used a superadditivity argument, you would replace it with this chain rule, which is an equality. And you may see intuitively why this will give you a lower bound for this problem, because the chain rule has this conditioning on the prefix, and this conditioning on the prefix exactly translates into Bob possibly knowing the prefix. Okay. Okay. Anyhow, there's more stuff on the index problem, believe it or not, fairly recently. So there's results by Manez et al. He's not here, right? He could have been. And there's results of myself and Kondapalli, where we talk about what if the parties are actually interacting. So Alice talks and Bob talks. You don't normally think of Bob talking in the index problem, but there are applications where it's important to understand what happens if Bob talks. Of course, Bob will only need to send a small number of bits, but anyway. Okay, so now, so let me tell you something about the history of information complexity at this point. So what I just showed you with the index problem from Ablayev's paper is probably the starting point of information complexity. He didn't actually use the term information complexity, but he used roughly this argument written in a different form. So the term comes from this paper of myself with Shi, Wirth, and Yao, and we actually define these terms, information cost and complexity, and this notation which we see today. And we used it to prove something that I'll show you in just a moment. Mainly for historic interest, but also it's a nice application of the paradigm. Okay, and it brings up 1 or 2 other ideas that will come up in more recent work. Now, one thing that I'm proud of, if I can toot my own horn for just a minute, is I'm not so much proud of, okay, I'm certainly proud of defining the terms, but I'm really proud that we said this in our paper, right? We actually said that this notion appears to be quite powerful and maybe of independent interest, which is, of course, words that are used in lots of papers about lots of things. But this time, I think we were right. So a year from, yeah?
Protocol independent proof is we should just use this in all papers.
Yeah. Okay. I see. Okay. Fine. So, so in this paper of Barrios et al., which really is, I think, the pivotal paper in information complexity, they saw, I would say, they started to realize the full potential of this idea. So they generalized these ideas to interactive communication, and they cleverly handled an issue that comes up when input distributions are not product distributions. All right. So with this idea of conditional information cost, we will see this later in the talk. Okay. And then more recently. So actually not so recent anymore, but in 2010, Barak, Braverman, Chen and Rao, they started the modern theory of information complexity by giving a really general definition that has led to a long line of what I call abstract results. So by abstract results, I mean results that apply to an arbitrary abstract function. Okay? So they're not trying to analyze any specific function, but trying to say something that holds in general. And we'll see what their main result was at the very end. Okay, so let's talk about simultaneous message communication. So let's recall a couple of things we saw in part 1, which is that we have this square relation between deterministic and randomized private coin complexity. And in particular, the equality problem shows you that this is tight. It has complexity square root n. Exactly, that's the tight bound. Okay, we saw both the upper and the lower bound. Now, we wanted to consider in our paper the following problem, right? Suppose we have m distinct copies of the equality function, okay, and then we want to compute not all the distinct copies, but just the OR of these copies. Okay, so another way of saying this is that Alice has m strings, Bob has m strings. Is it the case that one pair of strings is equal? Okay, so what is the randomized complexity of this thing? Now, if you use this method, then you can only get a bound of square root m times n, because the deterministic complexity is certainly at most m times n. But conceivably, you could have a direct sum theorem, which means that this m copies version is actually m times as hard as the one copy version. So probably this is the lower bound you should have, and we do have that. So that was sort of the main result of this paper, which introduced all these terms, information cost, complexity, etc. Let's see how we use the paradigm in that paper, right? Okay, so now let's say that Alice gets random input x and sends a message u, Bob gets y and sends v. We're going to define the information cost as mutual information between x and u and between y and v. Okay, again, the most natural definition. What does Alice reveal plus what does Bob reveal? Okay, now the simulation argument is going to be as follows. Again, we're going to design a protocol for equality by using a protocol for this bigger problem of OR equality. So as they did with the echo problem and index, Alice and Bob are going to plug their input into the ith position of this m copy problem, and then just fill the rest of the inputs at random, right? Now, there's a danger that when you fill the rest of the inputs at random, it's actually going to change the answer for the OR equality problem, right? It could be that by accident, one of these randomly filled positions makes the function 1 because those two inputs are equal. But this is unlikely, because if you fill things at random, then there's only a 1 over 2 to the n chance that the things will be equal, right? So there's at most m over 2 to the n chance that you destroyed your function by doing this. Okay, so let's say we can ignore that, and having ignored that, it remains to do step 3. So step 3, so step 1 and 2 together have shown us this, right? That the randomized complexity is at least m times the information complexity of one copy of equality. So it remains to show that the information complexity is at least the normal complexity. Okay, reverse inequality. So how do we do this? I will not show exactly how to do this, but I will just mention what is involved. So we want. So notice what we have to do. We want to read this statement as an upper bound rather than a lower bound. So instead of thinking that it's proving a lower bound on IC, imagine that it's proving an upper bound on R. Okay. So when you view it that way, what it means is we must somehow take a protocol which might communicate a lot but have low IC into one that actually communicates very little, right? So something proportional to its IC. So this is called compressing the message down to their information content. Okay? Now this idea, if you're familiar, if you're at least passingly familiar with the more modern work on information complexity, you'll see that this is the cornerstone of all that work, right? But in the simultaneous message setting without interaction, it was particularly easy to do this compression. And what we did was basically a form of rejection sampling to just sample messages from the original space. Okay, so I won't go into the technical details of this. I should point out that in subsequent work, a deeper version of this rejection sampling idea was used, and this goes under the name of communication complexity of correlation. I'm putting this out there to just say that if you're interested in knowing how this argument works, rather than read our paper, you should read this paper, which sort of does it in the right way and gives you a book proof. Okay, so let's talk a little about slightly interactive protocols. Okay, so I'm saying these are interactive, but they're not really interactive because we'll see that the way we apply the paradigm will be to more or less not worry about the interaction. Okay. So let me give you a motivating problem, after which I will state a communication result. So we want to prove, let's say, data structure lower bounds, right? As I said, you'll see a lot of streaming lower bounds during these 2 weeks, but maybe, well, you'll see a lot of streaming algorithms too, but not much about data structures. So maybe this will be the one time during these 2 weeks. So the general setup of a data structure problem is there's some data, Y, and you're going to pre-process this to produce a data structure T. You should think of T as a table. You'll see in a moment why. Later on, you get a query X, which is asking some question about the data Y. So your algorithm, of course, has to answer this query X by referring to this data structure T and then produce some output Z. And the output Z is deemed correct if a certain relation is satisfied. Okay, this is just an abstract notion of a static data structure problem. Okay, so let's take a couple of examples. So you can look at predecessor search, where your data is d-bit integers. The query is a single d-bit integer. And the goal is, what is the predecessor in the data? What is the predecessor in this data set of the query, right? So what's the number in the data set that is just before X? Okay. Another very important problem is approximate nearest neighbor search. I think Alex is actually going to talk about nearest neighbor search later on during this week. Maybe not about lower bounds, but anyway. So in nearest neighbor search, the data should be thought of as points, say in the d-dimensional Hamming cube. That's just one example of a metric space. It could be a different metric space. And the relation tells us that, well, this Z is a correct output if it's, say, beta approximate nearest neighbor of X with respect to Y. Okay? So beta approximate means its distance from the data set is at most beta times the distance of whatever the nearest neighbor would be. Huh? Okay. So to prove lower bounds for data structures, the standard model in which to work is the cell probe model. This is about the most general model you can imagine for a data structure type problem. So here it says that our data structure is just a table stored in cells in memory, and the query algorithm looks up cells from this table, right? So for instance, the query algorithm might look up the table at index I1, and it would get the table contents at I1, and then do it again with a different index, which may depend on the result of the first query, and so on. And after T such probes into the table, the algorithm would be ready with an answer. And the important parameters of this whole algorithm are, first of all, number of probes, that's the time. And then these two space parameters, but we're just going to say that this table should be of reasonable size, meaning it should have a polynomial number of cells. And each cell should be, say, poly d. So remember that each data point was d bits. So this poly d means that we don't allow a cell size which is much larger than the actual size of a data point. Okay, now this picture should be very suggestive, and it looks a lot like communication complexity, and it is, because you just call the left side Alice and the right side Bob, and there you are. So every cell probe algorithm really is a communication protocol. Okay, so now we come to the main idea. So this is this is Sudipto's favorite paper, which he was referring to a while back, the Milterson et al. Yeah. They get there. No, it is my favorite paper too. It's how I got started in this whole business when I was a grad student. So reading this paper and liking it a lot. Anyway, so the important idea for lower bounds on this is this thing called round elimination, where what we do is we have this protocol with multiple rounds, and we are repeatedly going to apply a certain argument that removes the first round of communication, and it also shrinks the instance size as it does so. Okay, so this is what may happen. So we have, let's say, we have a d-bit instance of our problem, and we remove the first round where Alice talks to Bob, and now we are solving somehow a d over k bit instance for some number k. Okay. And then we do the same from Bob's side. When we do it from Bob's side, then the number of points in the database shrinks. Okay, so the dimension is the same, but the points shrinks to say n over L. And so if you keep doing this, then because the original protocol had T messages each way, you find that eventually you've removed all the rounds, so you have zero communication, and you're solving an instance of size, well, of dimension d over k to the t, and with number of points n over L to the t. So if this instance is non-trivial, then you have a contradiction, because you shouldn't be able to solve a non-trivial problem with zero communication. So to prove a lower bound, all it remains to show is that, do the algebra and make sure that these numbers are non-trivial. So that translates basically into this query type. Okay, so you'll have to believe me on this translation, but this is just algebra. Okay, so now the question is, why do we have this shrinking behavior? So we have the shrinking. We certainly don't have it always, but we can prove the shrinking behavior when our problem has a certain embeddability property. So let me just try and explain with pictures what this embeddability property is. So remember how in the echo and index instance we were embedding an instance of echo into some position of the index problem. So this is something analogous to that. So we have a small version of the problem, let's say in a small number of dimensions, okay, and we embed it like this. We have some fixed prefix sigma, that we apply to everything, to the query as well as to every data point, and then we fill the sort of right end of things with random stuff. Okay, and it should happen that if say this one was a correct answer to the original instance, then it's still a correct answer to this embedded or padded instance. Okay. Now once we have this, then we can think of the simple task as our small instance and the complex task as our big instance. All right, and this big instance is roughly in some sense k times the simple task. Okay, the idea being that this gray stuff, which is the real input, could have appeared in one of several locations, or one of k locations. Okay. So all right, it remains to define information cost. So we have to make a careful definition here. So instead of looking at the information conveyed about the input by the protocol, we look at the information conveyed about the input by only Alice's first message, only the first message. Okay. All right. Now with that definition, one can do a simulation argument as before, more or less. So we generate this padding, right, where each of these xi's is a d over k bit chunk. So overall, we get a d bit instance. So if we had a protocol for the big problem, we now get a protocol. Well, we can now design protocols for the small problem. We go ahead and apply this kind of subadditivity, or in this case, chain rule, right? So it's just exact equality here. We have a number of terms. We have k number of terms. Each term has to be realized as the information cost of a suitable protocol, and you can check that with this padding, that's what happens, right? So anyway, the goal here is not to understand it line by line, but to just say that it's that same paradigm we saw before, but in a slightly more complicated situation. Okay. Now, what about that last step? So we need a compression argument. Okay. So what we've got so far is we have now this artificial protocol for a small instance, which invokes the protocol for the big instance and achieves therefore low information cost. Now, how do we achieve low actual cost? Right? So what it tells us is that the information cost is at most 1 over k of the original communication cost. Okay, so if our parameter k is chosen large enough, then we can ensure that this is little o of 1. Now, what does it mean that the information cost is little o of 1? If we go back and look at the definition, It's the information revealed by the first message in the protocol. So if that information revealed is little o of 1, so it's like a tiny amount, it's like no information has been revealed by this message, almost. Up to a small amount of additive error, it is the case that nothing has been revealed by the first message. So one thing we can do is we can modify this protocol slightly to say that, let's say the first message is sent on some other input x prime, which is completely independent of the actual input, right, but has the same distribution. So what we're saying is Alice, instead of sending her first message based on her input, just generates a new random input from that same distribution and sends the message according to that. So this message now has literally nothing to do with her input. So it has zero information about the input. Okay? And this modified protocol should still kind of work, because the difference between this original protocol and the modified protocol is only little o of 1 in some sense. Okay? And this can be made precise. We can say that the error is at most, or the statistical distance in fact between these two protocols, and therefore the error is at most square root of this information cost. Okay? The square root comes from Pinsker's inequality in information theory. Okay, so net result is we have removed one round. Okay, sorry. So hold on. We've removed one round, and we've therefore applied that scheme that I was showing you earlier of round elimination. That gives us lower bounds on the query time as before. Now one remark, that the approximate nearest neighbor problem doesn't really have this property called embeddability that I was mentioning earlier, right? I was saying that you should be able to pad the input with some stuff on the left and random stuff on the right, and it shouldn't change the answer. You can check that this is naturally true for the predecessor problem, because that is the way you compare two d-bit strings, right? If you want to numerically compare them. But if you want to look at this geometric notion of distance, like as an approximate nearest neighbor, it doesn't have this property, but it's possible to do a reduction from this kind of prefix matching problem with a larger alphabet. Okay, so I won't explain how that's done, because that's sort of nothing to do with communication complexity. But anyway, once you do that, you get something similar to what we were showing before. You can do the simulation argument, and you get a protocol whose information cost is like something like that, log n over k. But the value of k that comes up that you can use in this argument, it turns out once you do the algebra, is omega 1, right? Now we need this to be little of 1 in order to apply the idea I was showing before, that the first round is uninformative and just can be eliminated. Unfortunately, it isn't uninformative anymore, so we need some new idea. So the new idea is to use this communication complexity of correlation by Harsha et al. And to do a compression. And we compress that first message down to its information content. Okay? So we are unable to eliminate the first message completely, but we compress it down to its information content, which is somehow small. And once it's small, now there's some other combinatorial argument we can do to eliminate that message. Okay? So I'm not going into exactly how this is done. All I'm trying to say is that sometimes you can just delete the first message with tiny addition of error, but sometimes you do something just a little bit more sophisticated. Okay? So we compress it, and it doesn't go away, but we can then make it go away by doing something combinatorial rather than information theoretic. Okay, so this is admittedly kind of vague, but I just wanted to point out that there are some more steps involved in getting a nearest neighbor bound, and eventually we get this kind of bound. This result may be worth remembering. It tells us that with d dimensions in the Hamming cube, the time to do nearest neighbor queries is at least log d over triple log d. Okay? And that's actually tight, so there's a matching upper bound. Okay. Let me check one thing on the time here. Okay, given the time, I think I want to skip past this pointer jumping problem. All right. Sorry. So this is another instance of round elimination, which let me not do this. Let me get to this part. Okay. So I want to show you at least one example of this paradigm where we have full interaction. Okay. Because this brings up the full range of ideas involved in information complexity. So we look at the disjointness problem, which is again one of the basic and cornerstone problems of communication complexity. So the input here is a 2x(n) Boolean matrix, and the task, well, each row can be thought of as representing a set, subset of 1 up to n, and the task is to tell whether these sets intersect or not. But more specifically, we have a certain promise that either every column has weight at most 1, which means there's no intersection anywhere, or else one single column has weight 2, but everything else has weight at most 1. Okay, so either there's no intersection or there's a unique intersection. Okay, so make the first row an input to Alice, second row an input to Bob, and then this becomes a two-party communication problem. So we'll call it disjoint N2, and we'll generalize it at some point to T players. Okay. So here's how we see the direct sum situation in this case. So our basic problem. So let's look back at this picture. So the basic problem will be to take one column of this matrix and see what happens. So the task there is to determine whether in that single column you have 2 ones or not, right? So that's just the AND function. Okay. So so that's our simple task A, and our complex task B is to solve disjointness, which is like having n copies of n. Okay. Now there is a very important twist here. So the paradigm should apply more or less in the way you expect, except that in step 2, where you're doing the simulation argument, so far we've been plonking our input into one of the positions and then saying pad the rest of it at random, and things have more or less worked so far. But now they really won't work. It's severely wrong to do that, because if you just generate the rest of the columns at random without thinking, then of course you will turn every instance into an intersecting instance. And in fact, you will probably break this unique intersection promise of the problem anyway. So, okay. So we have to pad more carefully, and we must ensure that our padding columns, the other columns which are not the actual input, never have an intersection. Okay. So Alice and Bob must never generate 1, 1 on any of the other columns. Now the only way to do this is for Alice and Bob to have some shared randomness. If they did things on their own, then this is impossible to ensure. So here's what they're going to do. So we're going to have 2 distributions. So there's the input distribution x, y, and we'll also have these, well, I guess there's input distributions x, y, and we have some auxiliary random variables which I'll call d1 through dn. And so each xi, yi, di will have a certain joint distribution. Okay. So it's described in this picture. So d equals 0 tells us that Alice is going to generate a random input, whereas Bob is going to only generate 0. You can check that this is what's happening. If d equals 1, then Alice will always generate a 0, and Bob will generate a random input. So in fact, you should think of d equals 0 as d equals Alice, and this is d equals Bob, if you like. Okay. So we're going to make the following definition of information cost. The information conveyed by the protocol's messages about the input conditioned on these auxiliary random variables d, which tells us for each coordinate whether Alice was the one doing random things or Bob was the one doing random things. Okay. Now note that by design, Alice and Bob will never generate 1 and 1, right? So it ensures that our padding columns don't spoil our function. Okay. So the simulation argument will now proceed as follows. So we have a bunch of protocols for AND, right? Each of them will simulate a protocol for disjointness by doing this kind of padding. So use public coins to generate d, and then based on d we then generate x, y in each column according to this distribution, right? Now one crucial property of this random variable d is that for any column j, the d factorizes the distribution of x, y. So factorizes means that conditioned on each value of d, the distribution of x, y is now a product distribution, right? This is why Alice and Bob were able to generate things from x, y, d. Yeah? Once they know d, then Alice and Bob can work on their own. Okay. So now the algebra works out similar to how it's been working out before. The information cost of b breaks down into a sum, etc., etc. We have all of these nice things. Now finally, it remains to prove that there is a lower bound on the information cost of this AND function. Now as before, you could appeal to some kind of intuition and say that yeah, surely this can't be done with 0 cost. But let's see what's the precise argument for why it can't be done with 0 cost. Or rather, what is a particular constant that comes out of the argument? Okay. So now this may be a little bit heavy on the algebra, but let me try and walk you through this, because we do have just a little bit of time for this. So it's worth walking through at least this one basic example. Okay, so Here's the setup. We have a protocol for the AND function. We have this x, y, d distributed according to that distribution I was showing you. We have M, which is the distribution of the transcript. Okay, so whatever messages are sent in the protocol. So let's use the notation M superscript with 2 bits. So W and Z are 2 particular bits. So M superscript WZ means the transcript when Alice's input is W, Bob's input is Z, and then you use the same random coins to do whatever the rest of the protocol does. Okay, so the information cost by definition is this, okay, and I can split it in this manner: half of whatever happens when D is 0, whatever happens when D is 1. So far it's simple. Now, if you remember how the analysis for the echo function went, then this term is equal to a certain Jensen-Shannon divergence. Namely, it's the Jensen-Shannon divergence between the 2 possible values of M conditioned on D equals 0. So when D equals 0, remember that Alice is random and Bob is always generating a 0. So the 2 possible inputs are 0, 0 and 1, 0. Okay, so that's how you get this term. Similarly, that's how you get the other term. Okay, now we have to appeal to some analytic inequalities. Again, one of these calculus-based things. So the JS divergence is at least the squared Hellinger distance between distributions. Okay, this is again a basic inequality. So apply this to both the terms. Then over here we can use this triangle inequality like thing to conclude that this is at least quarter of this distance between 1, 0 and 0, 1. Okay, so again this is property of Hellinger distance. Okay, so what have we got? So we've lower bounded the information cost for our protocol by the something like the squared Hellinger distance between these 2 distributions. When Alice has 1, Bob has 0, and when Alice has 0, Bob has 1. Now, are these 2 distributions actually different from one another, or should they be? It's not clear because the answer is the same in both cases. See, they're trying to compute the AND the AND is 0 in this case and the AND is 0 in this case as well. So why should these be different? Okay, so it turns out that here we can use, we have to use the structure of a communication protocol, and we can do so to say that there's this cut and paste property. So we can take the 1 from here, cut it and paste it here, and exchange this 1 here with this 0 here, right? Okay, or it's like chromosome exchange if you like. Okay, so anyhow, so this is exactly equal to this because everything happened in a communication protocol. Okay. And once we have that, then it should be clear that these 2 distributions have to be far apart, because in one case the AND is equal to 0 and in the other case the AND is equal to 1. Okay. All right. So do I or don't I have that much time? Actually, not bad. 7, right? Okay, sure. All right. So let me walk you through just a little bit of this, because you've seen the ideas involved here. So we've seen before this private coin rectangle property, right? When we talked about the difference between private coin randomized and deterministic protocols. So the distribution of messages sent on a specific pair of inputs W and Z, that's the same as distribution of leaves in the tree version of communication complexity. This will factorize as some function depending on only Alice's input, some function dependent only on Bob's input. So something dependent on W, something dependent on Z, okay? And so, something got badly messed up here. They should be just P comma Q. I don't know why these extra parentheses came up, but anyway. Now the Hellinger distance by definition is this quantity, right? So this product here of P and Q together with this product nature then allows us to do basically simple algebra to see that, hey, these 2 things are the same. Okay. So that's really all it comes down to. The observation that we have this rectangle property that we saw before, and then the way Hellinger distance itself is defined, okay, it gives us this very nice property. Okay, very useful property. It's behind a whole bunch of other lower bounds that follow along these lines. So going back to this, if the error of the original protocol is at most epsilon, then the total variation distance between these 2 things must be at least 1 minus 2 epsilon. And then by yet another analytic inequality, this tells us the Hellinger distance must be at least 1 minus twice square root epsilon. Okay. So there are all these analytic inequalities that I'm throwing at you without saying why they're true, but trust me, in each case it's just a matter of, it's some function of one real variable, analyze it using whatever method you want and you get it. Okay. So overall, we've concluded that the disjointness function with error epsilon has at least this much complexity with this very specific constant in there, right? Yeah, by the way, that is not the best possible constant, but that's the constant that you get out of this argument. Okay. So there are many applications of the disjointness result, way too numerous to mention. But let me just try to say one thing that comes out of this kind of proof. One thing that easily comes out of this kind of proof is that if you generalize everything to t number of players, then well, you have almost the same argument as before will work, except that at the very end you need to understand what is the information complexity of AND with t number of players in it. Okay, and the answer to that turns out to be n over t. So this was proved in our initial paper for one-way protocols, and with a slightly weaker form for general protocols. And then Gronemeyer generalized the result fully to show that this is the case for arbitrary pattern of communication. Okay, so what this enables us to do is to address this classic data stream problem of estimating the frequency moments of a stream. So the frequency moment of a stream is defined as the sum of the kth powers of the frequencies of the individual items. Okay, this was known to require. This is known to be solvable in space n to the 1 minus 2 over k. This is a result of David and Indic, and now using this result, one can get a matching lower bound. Well, at least up to log factors. Okay. So I want to end by stating this one major result in communication complexity proven using basically this paradigm. Now this is an abstract theorem, so it's not a result about a concrete function, but it applies to a general function. And it says this is due to this landmark paper of Barak et al. One of the authors showed up. How did you appear? You weren't there. All right. You're always here. Okay. All right. All right. Okay. So good. Anyway, so what they showed, I assume you talked about this in detail earlier in the term. Okay. For the record, I guess that's Anup I'm talking to. Okay. So what they showed is if you take the basic direct sum problem, which is your basic task is you have some abstract function f, and your complex compound task is you have m copies of this, and you have truly m copies. You just want to output all the results of computing f on all the m pairs, all right? And you want to get each coordinate correct with some high probability, say 2/3 or whatever, right? So this is my m-fold task, and it should be m times as hard as the single task, but what they showed is it's something like root m times as hard as the single task. Okay? How do they do it? Guess what? It's the same paradigm. So they first define information cost. And their definition is kind of clever and does exactly the right thing. And there is a way to see what I just showed you with the Bar-Yosef et al. Argument using conditional information cost as also being an instance of this, okay? Up to some tiny modifications. So they define this notion which they call internal information cost. This time it's defined as the information that the protocol's messages reveal about Alice's input if you already know Bob's input. So this is what does Bob learn from the run of the protocol, and then plus what does Alice learn from the run of the protocol. Right? But now with that definition, we can do a simulation argument more or less as before using chain rule, etc., and then we arrive at this kind of an inequality. So the complexity of f to the m is at least m times the information complexity of f with respect to whatever distribution mu you may want to choose. Okay, now comes the really novel part of the argument, which is you have to obtain some kind of lower bound for IC, right? You have to obtain a reverse inequality, and as before, this amounts to compressing the protocol down to its information content. Okay, but what is new is that you have to do an interactive compression. So the compression results I was referring to earlier with rejection sampling were inherently of a non-interactive sort. So one message is being sent, and you need to compress that message to its information content. Now here you need to compress the whole interactive protocol down to its information content. That involves other new ideas, but I should point out that this is another instance of proving a lower bound via an upper bound, because the sort of the major part of this work is designing a certain protocol for performing this compression. Okay, anyway, so the compression result gives you something like this. It's perhaps not the optimal compression result. It's an open question if you can do anything better, and doing things better here will make things better up there. Okay, so I just wanted to put up an intimidating looking slide saying that there are tons of other applications of this whole paradigm. And there's just too many to go into. Maybe I'll do a little plug for a recent result of Braverman et al. And David, yes, I have lots of co-authors here. All right, so okay, so there's this recent result where they prove something like hardness of doing dimension reduction in certain statistical estimation problems. That is somebody going to talk about this, David? Do you know? He already did talk about it. Oh, okay, all right. Fair enough. So, okay. So, anyway, I wanted to put this up because it's from 2016. So, it's the newest result in this series. Okay. There's a whole bunch of results in quantum communication due to these authors over multiple papers that are using basically this paradigm but in a quantum setting where some things are far more complicated, but other things are just analogous. Okay. Thank you for your attention then.